Hey guys, in this video we're going to explore Vsepr theory and how it's applied. So Vsepr, what does it stand for? It stands for valence shell electron pair repulsion. And that's a really long name. But what the basis of this theory is this idea that in molecules there are electron pairs that you would find. They want to get as far away as they can from each other, and this is what gives rise to the three-dimensional geometries of molecules. If you want to have a good explanation and also visualization of the different 3D geometries, I would recommend going to this link here. I'll chuck that link in the description for this video. In this video they show all the three-dimensional geometries and how they come to be based on the number of electron pairs that exist around a central atom. But in this video that you are watching right now, what we'll be doing is working out how to apply Vsepr theory. So we will be working out basically the three-dimensional structures of various molecules. Okay, and in order to do this, we need to be able to interpret this kind of chart here. So this Vsepr geometries chart. In this chart here, we've been given a whole bunch of three-dimensional structures. They don't look three-dimensional on paper or on your screen because I mean, it looks kind of flat, but if you look at this kind of structure, for example, the tetrahedral structure, this wedge here that I'm coloring in, this sort of represents an atom coming out of the page. Like imagine it coming towards you, whereas this dashed line here represents an atom going into the board, going into the page. But if you watch the video that I've linked up here, you'll be able to make some sense of what these tetrahedral structures actually look like three-dimensionally. In any case, let's get going. So to define what a lone pair is a good place to start. Now a lone pair is basically a pair of electrons that are not involved in bonding. For example, in water looks like this. Around the oxygen atom, we have these here are the bonding pairs of electrons. So remember that those lines there, those lines connecting the oxygen atoms with the hydrogen atoms, represent bonding pairs of electrons or covalent bonds, electrons involved in covalent bonds. On the other hand, we have these pairs of electrons here that aren't involved in bonding. These are our lone pairs. So if we were to count the number of lone pairs around the oxygen atom in water, there are 2 lone pairs. Okay. Just give you a quick example to figure out for yourself. Here is ammonia. This is ammonia. I want you to just figure out for yourself how many lone pairs ammonia has. So you can pause the video to figure it out. So this is the only lone pair. In fact, ammonia has 1 lone pair. Okay. Alright, so hopefully at this stage we've established what a lone pair is. Let's have a look at the next learning objective, which is to define what steric number is, what it means. So steric number or alternatively the number of electron regions. The easiest way to define this is the steric number is perhaps this is not so much a definition as it is a it is a way to solve the steric number. But the steric number is the number of lone pairs plus a number of connected atoms. So number of atoms connected to the central atom. So what do we mean by this? So with water, the central atom is oxygen, okay? And if we're going to try and calculate the steric number of oxygen in water, we would have to combine the number of lone pairs with the number of connected atoms. So we know that oxygen has 2 lone pairs. Now we just need to work out what the connected atoms are. And we can see that connected to oxygen by covalent bonds, we have 1 hydrogen, 2 hydrogens. So there are in total 2 connecting atoms. And that gives us a steric number of 4 for water. So we've solved for the steric number of water, and we have the number of lone pairs of water. And these are all we need to work out the geometry of water, the 3D geometry. So if we use this table here, you can see that at the top of this table, we have each column separated by the number of lone pairs. So we want to look in this column here, the second lone pair, 2 lone pairs column, because we know that water has 2 lone pairs, okay? And then we want to find in which row does water fit. So water has a steric number of 4, as we've solved down here. So we go to this row here, steric number of 4. There's 2 lone pairs, steric number of 4. Water's shape is that it is bent. And this is indeed what water looks like in 3 dimensions if you ever look for a 3-dimensional model of water. What about ammonia? You have a go at working out the steric number of ammonia. So you can pause the video to figure that one out for yourself. But ammonia has 1 lone pair. So we go 1 lone pair plus number of connecting atoms. And there's 1, 2, 3 connecting atoms to nitrogen. So we can see that there's 3 connecting atoms, okay? Which makes the steric number 4, like water. So if we go to our table, 1 lone pair, steric number 4, this makes ammonia trigonal pyramidal. Trigonal pyramidal. Whereas water was bent. Okay. Let's do another example. So we have Ch4 Methane. Now, have a go at drawing the electron dot structure, so maybe pause the video to give yourself a chance to practice that. And methane will have a structure like this. Okay. Now, if we're going to use Vsepr theory to work out the 3D geometry of methane, we're going to do everything that we did before. Work out the steric number, work out the number of lone pairs. Then we can figure out the 3D geometry. So, number of lone pairs on carbon, the central atom, and the steric number. So feel free to pause the video again to figure these out for yourself, and also to figure out the geometry for yourself. The number of lone pairs, there are none, and the steric number of methane is 4. So if you go to your table, you would find that in the column with no lone pairs, going down to a steric number of 4, we get the tetrahedral tetrahedral shape. So methane is tetrahedral in three dimensions. Tetrahedral. Okay. Some additional examples that you can try. We have carbon dioxide here. And we also have BH3. Now this one's a bit of a tricky one. You'll find that with this particular molecule, boron only has 6 valence electrons after forming all its bonds. So it's a bit of an exception to most other atoms that try to seek an octet or a full outer shell. It's perfectly happy with just 6 valence electrons, so go with that. Now I'll give you the answers to these. Feel free to pause the video if you don't want to see what the answers are before you get to have a go. But BH3, the structure is, let me have a look. It will be trigonal planar. While carbon dioxide is linear. So hopefully you get those in your determinations of the lone pairs and the steric number. Alright, hope this helped. Thanks for watching. Bye.